Welcome to the Explainer. So today we're diving straight into one of the absolute most exciting challenges in AI right now: how to shrink massive, resource-heavy AI search models without completely breaking them. If you've been following the rapid advancements in information retrieval, you know we have some incredibly accurate models out there, but they come with a massive physical footprint. Today, we're going to explore a fascinating research paper that introduces a brilliantly elegant geometric solution to this exact problem.
And that brings us to the core question here. How do we actually make AI's search smaller without making it dumber? Because if you think about it, modern, highly accurate retrieval systems are kind of haunted by this fundamental storage bottleneck. They are incredibly smart, sure, but they require so much memory and computing power that deploying them at a massive scale is becoming a total logistical nightmare. We need a way to cut the fat without losing the precision that makes these models so valuable in the first place.
Okay, let's dive into this. Here's our roadmap for today. We'll start with the heavy cost of ColBERT, then look at why past pruning methods kind of fall short. After that, we'll introduce the Voronoi cell solution, figure out how to calculate token importance, and finally, look at some genuinely groundbreaking performance results.
All right, part one, the heavy cost of ColBERT.
So ColBERT is what we call a late interaction model. Now, instead of just squashing a whole document down into a single vector, it represents documents and queries as sets of token-level embeddings. It's basically doing this super fine-grained token-by-token matching, which is exactly why it gives us such fantastic, precise search results.
But, and there is a massive but here, because ColBERT stores a dense embedding for every single token in a document, the storage crisis is very real. The resulting index is just orders of magnitude larger than sparse or single vector models, literally a massive physical footprint. It creates this huge bottleneck if you want to deploy it at scale, driving up both memory requirements and computing costs. If you're running a dynamic database that's updating constantly, yeah, this sheer scale is a total deal breaker.
Which leads us to section 2, why past pruning methods fall short. To get what pruning is, just think about a sentence like, the capital of France is Paris. If you drop the word the meaning doesn't change at all, right? That's the whole goal here. We want to delete redundant tokens from the AI's memory to save space without actually losing any meaning. Historically, researchers have really tried two main paths to pull this off, but honestly, neither is perfect. First, you've got learning-free methods. These use basic statistical tricks, like just blindly deleting stop words or throwing out words that show up too much. And sure, they're fast, but they totally ignore how tokens actually interact with queries in the embedding space. A word that looks statistically unimportant might actually be absolutely crucial for one specific search. Then, on the flip side, you have learning-based methods. These use these clunky neural gates to try and learn what to drop. Better accuracy? Yeah, but they're slow, really expensive to run, and they frankly lack a solid theoretical foundation. Now, the most sophisticated attempt before now was something called LP pruning. The idea was to achieve mathematically lossless token pruning by using linear programming. Sounds great, right? Well, it had some fatal flaws. It forced vectors into these mathematically destructive non-unit norms. And worse, the computational demand was just off the charts. Trying to run this on huge document collections was practically impossible because it was just so incredibly slow. So what's the fix? Let's move to section 3, the Voronoi cell solution. The researchers behind our source paper summed it up perfectly right here. They wrote, by interpreting each token's influence as a measure of its Voronoi region, our approach enables principled pruning that retains retrieval quality. Instead of relying on random linguistic guesswork or those slow neural networks, they decided to look at the literal hyperspace geometry of the AI's memory. Pretty wild, right? So to really grasp this, we need to know what a Voronoi cell actually is. Imagine the AI's embedding space is this giant, sprawling map. A Voronoi cell is basically a specific territory on that map where a given token acts as the primary landmark, meaning it's the exact region where that specific token is the absolute best, top-scoring match for any query that happens to land there. It's honestly a brilliant real estate metaphor. Token importance is quite simply the measure of its Voronoi territory. If a token commands this massive stretch of embedding space, it's a vital landmark. You absolutely cannot touch it. But if a token's geometric real estate is tiny, well, that means it almost never acts as the best match for a query. So it is completely safe to demolish without ruining your search results. All right, let's get into the mechanics. Section 4, calculating token importance. The researchers cooked up this 4-step algorithm to do this super efficiently on modern GPUs. Step 1 is Monte Carlo estimation. Since you obviously can't map out an infinite query space, they sample tens of thousands of random queries to estimate the size of each token's territory. Step 2 is iterative token removal, where they prune the absolute weakest links. Step 3 takes this logic global, scaling it across the entire document corpus to find the least important tokens everywhere. And finally, Step 4 uses specific search strategies to refine the selection, just making sure the cuts they're making are absolutely optimal.
I really want to emphasize that second step, the iterative part, because it is incredibly important. You might be wondering, why not just measure the territories once and delete the bottom 50% all at the same time? Well, it all comes back to geometry. When you demolish a landmark, the borders around it actually shift. Queries that used to point to that deleted token now have to find a new nearest neighbor. If you don't iteratively redraw the map and recalculate those territories after every single removal, you're going to blindly destroy important data and totally wreck the model's accuracy. To make sure they're making safe cuts, the algorithm tracks something called mean error, or ME. And this is really cool. The researchers found that this mean error has a near-perfect linear relationship with the retrieval performance after pruning. By tracking this one single metric, they get a super reliable mathematical proxy to guide their cuts. Literally no guesswork involved. The math tells them exactly what quality they're trading for space.
Okay, let's look at the payoff. Section 5, groundbreaking performance results.
Now, what's really interesting about the numbers here is just how staggering they are. Look at this, a 120 times speedup compared to that old LP pruning method. Because this new algorithm relies on simple dot product operations that modern GPUs just absolutely chew through, rather than complex linear programming, it is insanely fast. To put that 120x speedup into a real-world perspective, let's look at the MS Marco dataset. We're talking 8.8 million documents here. If you tried to prune that collection with the old LP pruning method, you'd be sitting there for 15 straight days of continuous computing. Voronoi Pruning? It knocks the exact same job out in just 3 hours. If you're a company running a dynamic database that updates constantly, a 15-day pruning cycle is just completely useless. A 3-hour cycle? That's a real game changer. Of course, being fast doesn't mean anything if the search gets dumber, right? But check out the retrieval accuracy in that MRR at 10 column. The massive, unpruned ColBERT model scores a 39.7. When we use Voronoi Pruning to literally chop the database in half, a 50% pruning ratio, the score only drops to 38.9. That just blows the older heuristic methods like FirstPick or IDF completely out of the water. We're cutting storage costs in half and barely even putting a dent in performance. But what if we get a little crazy and push it to the absolute limit? The researchers wanted to see what happens when you chop away up to 90% of a document's tokens. Imagine that, only retaining a tiny 10% fraction of the original data. Actually, scratch that. Let's go even further. Look what happens at just 6% of tokens retained. The old LP pruning completely falls apart. Its accuracy score crashes down to 0.46. But Voronoi pruning, its stability is just unreal, holding incredibly strong at 0.67. Because it actually respects the geometry of the embedding space, it keeps those vital landmarks intact, even when the map is almost entirely erased. So this elegant, math-driven approach doesn't just solve the storage bottleneck for late interaction models. It fundamentally reframes how we think about neural memory. And it leaves us with this really provocative question to close on. If hyperspace geometry can so effectively solve the massive AI search storage crisis, what other massive AI bottlenecks could it demolish next? The boundaries of optimization are absolutely being rewritten, and the future is looking incredibly geometrically precise. Thanks so much for joining me for this explainer, and we'll catch you next time.